Close your eyes for a moment. Listen. You might hear traffic sounds, the hum of a computer, or simply the silence in the room. But if you could hear the tiniest things, if your ear could sense the most fundamental vibrations of reality, you would hear something extraordinary. You would hear the music of the universe because, according to the most ambitious theory of modern physics, everything that exists is essentially music. Your body, the chair you're sitting on, the stars in the sky, and the light shining on your face. All of that is nothing but music. Vibrating strings in hidden dimensions are playing the symphony of existence. This idea sounds crazy, but it might be the key to finally understanding why the universe exists and why there is something rather than nothing. But before revealing why this theory upends everything we thought we knew about reality, we first need to understand the problem it is trying to solve. It is a problem so profound that it has haunted the greatest minds of our time, a problem that forces us to rethink the nature of space, time, and matter. Imagine you are a detective facing an impossible crime scene. You have two completely reliable witnesses, but their testimonies completely contradict each other. The first witness describes a world where everything is predictable and every outcome has a clear cause, where space and time form a smooth fabric called space-time. The second witness speaks of a chaotic world where particles appear and disappear without reason, where reality seems fuzzy and uncertain. And that is exactly the situation modern physics has faced for a century. We have two extremely accurate theories that seem to describe two completely different universes. On one side is Einstein's general relativity. This theory tells us that space and time are not a fixed backdrop but a dynamic fabric that bends under the influence of matter and energy. This curvature is what we perceive as gravity. When you fall, you are simply following the geometry of space-time. This theory works perfectly to describe planets, stars, galaxies, and even the entire universe. On the other side, we have quantum mechanics. This theory reveals that in the microscopic world, reality operates by completely different rules. Particles can be in many places at once. They can tunnel through impassable barriers. They can influence each other instantaneously across space. This theory perfectly explains the behavior of atoms, electrons, and all the forces of nature except one. That force is gravity. And here is the problem. These two theories, the pillars of modern physics, are incompatible. When you try to combine them, when you apply quantum rules to gravity, you get nonsensical results. Infinite infinities everywhere. Meaningless calculations, impossible predictions. It's like you have two perfect languages to describe reality, but they come from completely different planets. How do you translate from one language to the other? How do you reconcile the irreconcilable? For decades, physicists searched for a solution. They imagined increasingly complex theories, explored ever more abstract mathematics, but nothing truly worked. Until one day, a young Italian physicist, in 1968, made a discovery that changed the course of physics. He wasn't trying to revolutionize our understanding of the universe. He was simply trying to solve a technical problem about nuclear particles. What he found was far greater than anyone imagined. He discovered that reality might be made of music. The year is 1968. Gabriel Veneziano, a 26-year-old young physicist. He was working in his office at the University of Turin, tearing his hair out over a problem that had haunted physicists for years. How to explain the strange behavior of particles inside the atomic nucleus. These particles, called hadrons, behave strangely. When they collide, they don't bounce off each other like billiard balls. They seem to dance together, exchanging energy in mysterious patterns, creating new particles according to rules no one understood. Veneziano was searching for an equation, a mathematical formula that could describe these interactions. He had tried every classical approach, but nothing worked. Then, in a moment of creative desperation, he remembered an old mathematical formula he had learned in college. The Euler beta function, invented in the 18th century to solve geometry problems, had nothing to do with particle physics. It was an abstract mathematical tool, a historical curiosity. But Veneziano said to himself, "What if I try this just to see what happens?" He took the Euler function, adapted it to his problem, did a few calculations, and lo and behold, not only did it worked extremely well. The formula accurately predicted the behavior of hadrons with astonishing precision, but there was a problem, a big problem when Veneziano analyzed his formula thoroughly. and he realized that it did not describe point particles as everyone thought. It described extended objects, like fibers, like strings. You really need to understand that surprise. It's a bit like you're investigating why a ball bounces, and you suddenly discover that the ball is not a sphere, but actually a violin string. No one took this idea seriously. Strings in the infinitesimally small world. That seemed ridiculous. Particles are points. Everyone knows that. This story about strings must be just a mathematical phenomenon, a quirk with no physical meaning. Many other physicists began to delve into this problem all over the world, and the deeper they dug, the more they discovered something extraordinary. These strings are not ordinary objects. They vibrate, and depending on how they vibrate, they give rise to different particles. It's a bit like a guitar string. Depending on the note you play, it produces different sounds, and the same thing happens here, except instead of musical notes, the cosmic string produces different particles. A string vibrating in a certain way becomes an electron. The same string, vibrating differently, becomes a photon, a quark, or any other particle. The entire diversity of matter is nothing but different notes of a cosmic instrument, and that was just the beginning. Because when physicists pushed this idea to its limits, they discovered something even more astonishing. To understand what is about to happen, we must first take a journey into the subatomic world, a journey so deep that we will touch the limits of existence itself. Imagine you could shrink down multiple times until you are smaller than an atom. First, you would see electrons dancing around the nucleus, a bit like planets orbiting a star. Then you dive into the nucleus, you would discover protons and neutrons squeezed together by the nuclear force. But keep shrinking, dive into a proton, and you would discover that it is not just a simple particle. Rather, it is a collection of smaller particles, quarks. These quarks are bound together by other particles, gluons, in a frenzied dance of pure energy. But we still haven't reached the bottom. Continue shrinking to a scale so small that it takes 35 zeros after the decimal point to represent it in meters. You reach what is called the Planck scale, the smallest distance with physical meaning. And there, according to string theory, you will discover the ultimate truth about reality. You will no longer see point particles, those dimensionless points we have imagined for a century. You will see filaments, loops of pure energy, strings vibrating in a space completely different from what we know. Because this is the most unsettling secret of string theory. These strings do not vibrate in our three-dimensional space. They vibrate in a space with 10 or 11 dimensions, depending on the version of the theory. But wait, 10 dimensions? 11 dimensions? Where are these extra spatial dimensions? Why can't we see them? Yes, that's when things get really interesting. Because according to string theory, these extra spatial dimensions are all around us all the time. They are compactified, curled up on themselves at a scale so small that we cannot even perceive them. To understand this idea, imagine looking at a garden hose. From very far away, it looks one-dimensional, somewhat like a line. But if you get closer, you will discover it actually has 3 dimensions: length, width, and height. Width and height were hidden by the same distance. Our space may have invisible hidden dimensions because they are curled up at the Planck scale. At every point in our 3-dimensional space, there would be an additional 6 or 7 spatial dimensions curled up in extraordinarily complex geometric shapes. These shapes have a name, Calabi-Yau manifolds, named after the mathematicians who discovered them. They are very complex geometric objects. Computers are needed to visualize them, shapes that challenge the human imagination. But here is the most extraordinary thing. The way these spatial dimensions are curled up determines the laws of physics that we observe. It's as if the universe is a cosmic origami, and each different fold gives rise to a universe with different laws. But why so complex? The answer brings us to the issue we mentioned at the beginning, the unification of forces. To understand why string theory needs all these dimensions, we first have to understand what it is trying to achieve. It seeks to unify all forces of nature into a single coherent description. In our universe, there are 4 fundamental forces, 4 ways that matter can interact with itself. For a long time, these forces seemed completely different, with no relation to each other. First, there is electromagnetism, the force that makes your electronic devices work, holding electrons around the atomic nucleus. This is a long-range force that can act through empty space. And then there is the strong nuclear force, the force that holds protons and neutrons together in the atomic nucleus. This is the strongest force in nature, but it only acts over very short distances. There is also the weak nuclear force, responsible for certain types of radioactivity. It is weaker than the strong force and acts over even shorter distances. And finally, there is gravity, the weakest force of all, yet it dominates on large scales. Because it acts on all matter and energy, for a long time these four forces seemed unrelated to each other. But in the 20th century, physicists began to discover hidden connections. First, they realized that electromagnetism and the weak nuclear force are actually just two aspects of the same force called the electroweak force. At very high energies, these two forces behave identically, and then they discovered that the strong nuclear force can also be unified with the electroweak force in the so-called grand unified theory. But gravity resists. It stubbornly refuses to unify with the other forces. Every attempt ends in failure. Every calculation seems impossible and yields absurd results. And that's when string theory emerged. Because in this theory, the four forces are not separate entities but different manifestations of a single phenomenon, the vibration of strings. Imagine a cosmic violin. Depending on the note it plays, it produces a different force. Some vibrations produce electromagnetism, others produce the strong nuclear force, a third produces the weak nuclear force, and the fourth force is gravity. But for this symphony to work, every note must be played by the same instrument. The instrument must have enough strings. And that's exactly what the extra dimensions provide, the necessary space for the strings to vibrate in all required modes. Like wanting to play a Beethoven symphony on a violin with only one string, it's impossible. You need many different strings tuned differently to create all the harmonic richness of music. The universe needs many dimensions to create all the richness of physical phenomena. The problem is that this unification comes at a price some physicists consider too high. When physicists began exploring string theory seriously in the 1990s, they discovered something troubling. This theory, which was supposed to provide a unique and elegant description of reality, seemed to predict an infinite number of possible universes. The problem comes from the way the extra dimensions can be curled up. There is not just one way to fold the cosmic origami. There are billions, trillions of ways. In fact, according to the latest calculations, there could be 10 to the power of 500 ways to curl up the extra dimensions. To help you visualize this staggering number, know that there are only 10 to the 80th atoms in the observable universe. The number of possible universes in string theory far exceeds the number of atoms in our universe. Each different way of rolling up the dimensions creates a universe with different physical laws. In some universes, electrons would be heavier. In other universes, gravity would be stronger. In still others, there might not even be any atoms, only an ocean of exotic particles. This is called the string theory landscape, and this landscape poses a fundamental problem. If all these possibilities exist, how do we explain why we live in this universe and not another? Some physicists have proposed a radical answer. Perhaps all these universes actually exist. Perhaps our universe is just a bubble in an infinite cosmic ocean where every possibility is realized somewhere. That's the idea of the multiverse, a dizzying hypothesis. According to this, our reality is just one note in an infinite cosmic symphony where every possible melody is played simultaneously. But other physicists find this idea deeply unsatisfying. If everything is possible, then nothing can be predicted. If every physical law exists somewhere, the theory loses its explanatory power. It becomes a theory that explains everything and therefore explains nothing. This is one of the great debates animating modern physics. Is string theory a scientific theory, or has it become a form of mathematical metaphysics? To understand the scale of the controversy, we must go back to the foundations of the scientific method. What makes a theory scientific? What simply distinguishes it from philosophy? According to philosopher Karl Popper, a theory is scientific only if it can be falsified, meaning it makes precise predictions. These predictions can be tested and potentially refuted by experiment. Einstein's theory of relativity, for example, predicted that light would be bent by gravity. This prediction was tested during the 1919 solar eclipse. It was proven correct. Quantum mechanics predicts phenomena such as quantum tunneling or entanglement, which have been observed in laboratories. But string theory, after more than 50 years of development, has yet to make any testable predictions. The energy required to directly observe strings is so high that it far exceeds the capabilities of our particle accelerators. One would need to build an accelerator the size of the solar system to have a chance of observing a single string. This has led some physicists, such as Peter Volta from Columbia University, to declare that string theory is not even wrong. This is an allusion to physicist Wolfgang Pauli's remark about a particularly mistaken theory. It's not even wrong. It's too vague and untestable. Lise Moline from the Perimeter Institute has written an entire book about what he calls the problem of physics. He accuses string theory of diverting an entire generation of physicists onto a dead-end path. But the defenders of string theory are undeterred. Edward Witten is one of the world's most respected physicists. He argues that the theory has provided deep insights into the nature of reality, even if it has yet to make any testable predictions. And then there are recent developments that have rekindled hope for string theorists. One of the most surprising discoveries in recent decades is that string theory, though not directly testable, has found applications in completely unexpected fields. In 1997, Rohan Maldacena, an Argentine physicist, made an extraordinary discovery. He showed that a string theory in 5-dimensional space is mathematically equivalent to a quantum field theory, which holds in 4-dimensional space. This discovery, known as the ADS-CFT correspondence, revolutionized our understanding of the relationship between gravity and quantum mechanics. It suggests that information contained in a volume of space can be completely described by encoding it on a surface, like a hologram. This holographic idea has profound applications. It suggests that our 3-dimensional universe might be just a projection of information stored on a 2-dimensional surface at the edge of the cosmos. We are all holograms, but unaware of it. More concretely, this correspondence has allowed physicists to use string theory to solve problems in other fields. For example, it has helped understand the behavior of certain high-temperature superconductors, a crucial phenomenon for the development of new technologies. It has also enabled progress on one of the most difficult problems in physics, understanding what happens inside a black hole. Thanks to the holographic correspondence, physicists can now study black holes by analyzing simpler quantum theories. These applications show that string theory, though it hasn't fulfilled its initial promises, continues to generate valuable insights. It has become a powerful mathematical tool, even though its status as a fundamental physical theory remains controversial. But perhaps there is a deeper reason why string theory continues to captivate physicists, a reason that goes beyond equations and experiments, touching something fundamental in human nature. There is something deeply satisfying in the idea that all the complexity of the universe could arise from a simple principle. All the diversity of matter, energy, every force, every particle, just different notes of a cosmic melody. This quest for unity is not new. It originates from Greek philosophers who sought the fundamental element from which everything else is made. Thales thought it was water, and Anaximenes believed it was air, and Heraclitus leaned more towards fire. But it was Pythagoras who had the deepest insight. He discovered that musical harmonies correspond to simple mathematical ratios. A note an octave higher has exactly double the frequency, and a perfect chord corresponds to the ratio 3, 4, 5. This discovery led him to a revolutionary idea: all is number. He believed the entire universe is built on mathematical principles. The planets themselves, in their orbits, produce a music of the spheres, inaudible to the ear, but perceptible to the mind. This Pythagorean vision inspired generations of scientists, and Kepler sought harmonies in planetary orbits. Newton discovered that the same law governs the fall of an apple and the motion of the moon. Einstein dreamed of a unified theory that could reveal the hidden harmony of the universe. String theory is the direct heir of this tradition. It tells us that the universe is literally created from music, that each particle is a note in a cosmic symphony, and that the laws of physics are nothing but the rules of universal harmony. If string theory is correct, then every atom in your body is a note in a cosmic melody. Your heart beats, your neurons fire, your cells divide. All of that is just music, variations on a universal theme. And when you listen to a symphony by Beethoven or a song that moves you, Perhaps you are just recognizing an echo. From the deepest nature of yourself, you hear the universe singing within you, and you are singing along with the universe.